Welcome to another hot and sunny day in Thailand, and today we're going to focus on reference voltage. And it may seem like an arcane topic, but I'm telling you, this is key to everything I've done and everything I realized I've done wrong in my project so far. Some of you may have already figured it out, but sometimes experience comes with looking at things and seeing it's not right, and then lots of swearing, and then you figure it out. So, voltage reference. When we want to use our C21 chip to read an analog voltage, you'd think, that's simple. I put a AA battery on some pins that reads me 1.5000 volts, if that's what the battery's voltage was, as confirmed with, say, a fluke meter that I happen to have on my test bench. That's not remotely how it happens. What you have to do is tell the analog to digital converter, this guy right here, what range of voltages it should be calculating against, or the term is quantizing. And what it does is it breaks up from this voltage to this voltage in some number of discrete points. Now we're working with a 12-bit ADC on my C21 chip. So it's breaking up this range of voltage into 4,096 different points, which is great. But what is our reference voltage? Now, this is a, do dogs think about God kind of question, but it's critically important because the way I've wired up the circuit board so far is my top voltage up here, the reference voltage, is whatever my 5 volts is on the board. But I've come to realize that that's crap. That is not a good enough voltage, because if I've got 12 volts wired into the board and I'm going through my 5-volt regulator, that thing is plus or minus 3%, and I cannot deal with my voltage reading being off by plus or minus 3%. And if I'm coming in and I've got the USB cable plugged in, that could be crazy. That could be anywhere from 4.5 volts up to 5.5 volts, and that's even worse. So what I need is a very, very, very accurate reading up here as the top of my voltage input, so the ADC can accurately calculate the steps in its voltage reading and deciding how to distribute those 4,096 points. Because if the voltage here is actually 4.5, those 4,096 points are going to be a little bit closer together. And at 5.5 volts, those 4,096 points are going to be a little bit farther away, which means I can't trust the math that I want to do to give me a good voltage reading. Now, the interesting thing is the AppMelt chip allows us to choose from one of several different reference voltages. So it's trying to help us give us the most flexibility that it can to decide how to chop up those 4,096 points across a voltage range. Now, we'll go down to the bottom. VDD-ANA, that's my analog voltage running the board. Right now, that's flopping around, 5 volts plus or minus some unknown value. I cannot count on that. Related to that, there's this it took me a while to figure this out. It's basically the analog voltage divided by 1.6. I don't know how they chose that number, but it's going to give us roughly 3.125 volts. But it's still roughly 3.125 volts. It's depending on the voltage that's driving the chips on the board. Here, we have 1/2 of VDD-ANA, so that's going to give us roughly 2.5 volts. Still not accurate enough for what we're looking for. Here, DAC internal output. That's digital to analog converter internal output. One of the things that this chip has is it can turn a digital number, say 897, and generate an analog voltage that represents that number. It's the exact opposite of an ADC. And the chip has the capability of doing kind of a fake DAC value. You write to a DAC value, and then you internally read it back in as your ADC voltage reference, which sounds great, except the DAC needs a rock solid voltage reference that you trust. And I don't have one. Now, this internal band gap reference, this is very, very badly documented, but it lets you select an internally regulated voltage reference. And this is a real reference. And from what I can see in the documentation, there are three values: 1.024, 2.048, and 4.096. And those are nice powers of 2. The 4.096 would be really good, because it's a little bit less than 5, and it would let me do my math against that scaling value. By choosing the internal band gap reference, I have a good reference, but it's still not calibrated against the voltages that are going to be hitting that pin. Now, I could get close by choosing my resistor values for the voltage divider, but the top value driving the voltage divider is not going to be accurate. And then also, the voltage that's driving the ACS770 chip, I've got that tied to plus 5 volts right now. So therefore, I cannot depend on that value being accurate, and it's going to max out at around 5 volts, which is greater than the 4.096 volt value that I'm going to be working against here. So I would have to artificially limit my current, or otherwise we're just going to peg out that value at 1111111, like the top value. Or I have another choice. So there exist in the world these things called voltage regulator chips. They're generally very tiny. Well, that one's a little bigger, but this little surface mount guy is cute. They're tiny, they're cheap, and they do the job. And what I need this tiny to do serves two purposes. One, it will be the supply voltage for the ACS770 current sensor, and that will be its maximum possible input value. Therefore, I can do the math to calculate current from that, and I know it'll be accurate. Then the chip will also drive the analog reference voltage pin of the C21, and when I say I want to measure voltage with respect to the external reference voltage pin on the chip, I know everything's working from exactly some voltage. Therefore, the ADC will spread its sample values out exactly the way I want to be reading my voltages. Now, the question is, to get the maximum possible value, or the highest, I don't even know the word, resolution is not quite right, but if we were to take 5 volts, a 5 volt chip like this, it would be divided by 4096, and that would be the sample size that I could get out of this board, a theoretical maximum. But generally, you can't drive these chips with a voltage that's very, very, very close to the voltage that you want it to output and be super, super accurate. So especially if the voltage is lower. If I'm getting 4.5 volts out of my USB cable, and I'm asking this guy to give me 5.0000 volts out, it's not going to work. So worst case. And if you think back to that 4.096 value that the C21 can internally generate, it turns out that's a very popular voltage regulator voltage for high accurate voltage sensing. So let's take a look and see what we have on the market that will do the job for me. So here I am on my RS Components website. There they have a giant warehouse in Bangkok, so I can get parts really fast, and it's very, very comprehensive parts catalog like Mauser or one of the big American suppliers. Now I've gone into voltage references and I've specified some search criteria. The first one is I want my nominal output voltage to be 4096 volts. Matching that up with our 12-bit ADC, which gives 4096 bits of resolution, that means every bit number coming out of the ADC represents 1 millivolt, and that makes the math really easy. For accuracy, I decided I don't want to go any worse than 0.2%, and there are some ones that are quite a bit better. I definitely want a surface mount chip, and it needs to be able to provide current to drive both the ACS770 and the analog reference input pin to the C21. Now the ACS770 spec sheet says it needs 10 to 15 milliamps to run, and the C21 says it needs like 1.5 milliamps maximum on that voltage reference pin. So I'm looking at 25, 30, and 100 milliamp output chips. And when I apply that, we get 19 chips back. And I've sorted on price. And here, the first one is 26 baht, which is about 83 cents. I can live with that. It's actually made by Microchip, which is the same company that makes our C21 chip. So I think I can trust them. Or at least back in my IBM days, we called it one throat to choke when something goes wrong. But that comes in a tube of 100. I don't think I need 100 of them. And if I look down here, it's the same chip, but I can buy them by the tens. And it only goes up by 0.7 of a baht, which is about 2 cents. So that's really good. So let's go and check out the specs on this chip. Okay, here we are in the spec sheet for the MCP1501. It is a high precision buffered voltage reference. Initial accuracy of 0.08%, which represents 0.82 millivolts. So at most, I'm going to be off by just about 1 tick out of 4,096 samples. So this is just about 1 millivolts worth of error that I can expect. And we're doing the 4096 volt chip. And if we look down here, this is the chip that we're working with, an 8-lead SOIC surface mount, and it's got some obvious connections. This is the input voltage, this is the output voltage, this is ground, ground, and ground. This feedback pin, as I read later on, gets connected to the out pin, and that drives kind of an internal feedback loop to make sure that the voltage is staying accurate. This pin is not connected, and this is a shutdown pin which helps the chip go to sleep and cuts down its power consumption. If you have a sleep facility in your circuit, you'd want to use this chip, this pin. Otherwise, we pull it up to plus 5 volts and tie it to pin 1, and it will never go to sleep. And as you can see, our chip is the MCP1501-40. It can take from 4.3 to 5.5 volts, which is perfect. That's about a little bit lower and a little bit higher than what I think our worst case scenario is. And if we scroll down, the output voltage of the MCP1501 is 4.0925, absolute minimum, 4096 typical, and 40995 maximum. So that's great. And these super nice engineers have also given us a sample schematic to be an A to D converter reference. because they know how important it is. Here we have a 2.2 microfarad capacitor between power and ground. That gives a nice clean DC signal into the chip. The output of the chip, they've got a 1 kilo ohm resistor between power and ground, and a 1 kilo ohm and a 2.2 microfarad capacitor also between output and ground. And these contribute to adding high frequency noise filtering to the output, which gives us a rock solid, no ripple DC, highly accurate voltage reference signal going into one of the other A to D converters in the microchip family. And now for our next round of masochism, we get to go back into Atmel's start and tell it what our plan is. So we come down here. For current, we're still reading one signal, asynchronous on ADC1. We want to read from that input pin to ground, which is fine, but we need to change our reference to external reference A. And what that does is that's what's called VREF A in the rest of the documentation. So we'll go ahead and save that. Then we come over to our voltage reading system. Now, in a bit of foreshadowing, we were looking at using analog input 0 and 1, the simplest first two inputs, for our differential voltage reading. And we come down here, and I've already set our external reference A here. But the problem is the external reference A takes the pin away for PA03. There's only one VREF A chip on my C21, and it is a duplicate of analog input number 1, which is this guy right here. So basically I want to say, yes, I need to assign that, and then I need to change my other differential input to PA04, which is pin 5, which is currently unused. And we go from analog input 0 to analog input 4 with external reference A. Now, this has, of course, pretty massively changed the circuit board design by adding a whole chip and moving around these analog input pins and the UART pins. So I'm going to take a breath. I'm going to order the voltage reference chip, probably get 20 of them for fun, and I'm going to do a new spin of the circuit board and get myself back to a place of stability. One thing I do want to go through, though, is work on the CANbus, because there may be a problem with that I need to find out about. Hopefully it's just dead simple. So the next video will be CANbus on this current board, and then I'm going to respin the board and send it off to China. As you stare out on my beach, I would ask you to subscribe to my channel and click like on this video so YouTube thinks I'm worthy again, and I have so many people on my channel that they'll give me 10 cents a day in ad revenue. So I thank you for that.